Hello, everybody. This lecture is about corona. Corona is an important phenomenon in the mechanical and electrical design of overhead transmission lines. It occurs when the electric field intensity around a conductor exceeds the dielectric strength of air, causing ionization of the surrounding air molecules. So this result in found violent glue, hissing noise, ozone formation, and power losses. Corona is more likely to occur in high voltage transmission lines, especially under bad weather conditions such as rain, fog, or dust, and when the conductor surface is rough or irregular. From a design perspective, you need to try to minimize corona effects by increasing conductor diameter, using bundle conductors, and maintaining proper spacing between conductors. Reducing corona is essential because it improves transmission efficiency, reduce radio interference, limits energy losses, and extends the life of insulation systems. Therefore, understanding corona is a key part of designing reliable and efficient overhead power lines. So in this presentation, I will begin with a brief introduction to the corona phenomena in overhead transmission lines and explain why it is important in power system design. Next, we will discuss the main factors that affect corona formation, such as conductor size, spacing, surface condition, and atmospheric conditions. After that, we will define the important technical terms related to corona, including disruptive critical voltage and visual critical voltage. We will then examine both the advantages and disadvantages of corona, since it can have both beneficial and harmful effects on transmission systems. Finally, we will review the common methods used to reduce the corona effect and improve the efficiency and the reliability of overhead transmission lines. Okay, when an alternative potential difference is applied across two conductors with a spacing much larger than their diameters, and the applied voltage is relatively low, the surrounding atmospheric air remains unchanged and acts as an insulating medium. Under these normal conditions, no visible or audible effect is observed around the conductors. However, as the applied voltage gradually increases, the electric field intensity around the conductors also increases. Once this electric field becomes strong enough to exceed the electric strength of air, the air surrounding the conductors becomes ionized. So this ionization leads to the phenomenon known as corona, which is usually accompanied by a faint violet glow, hissing sound, ozone production, and power losses in the transmission lines. When the applied voltage increases behind a specific limit known as the critical disruptive voltage, the electric field around the conductors becomes strong enough to break down the insulating property of air. As a result, the air molecules around the conductor become ionized, and the conductors are surrounded by a faint violet glow known as corona. This phenomenon is not only visible but is also associated with several noticeable effects. Corona produced produces a hissing sound due to the rapid movement of charged particles in the air. So it also leads to the formation of ozone because of chemical reactions in the ionized air. In addition, corona causes power losses in the transmission line, which reduces system efficiency and it created radio interference that can affect nearby communication systems. As the transmission voltage is increased further above the critical disruptive voltage, the effects of corona become more intense and more noticeable. The faint violet glue around the conductor expands, forming a larger and brighter luminous envelope surrounding the line. At the same time, the hissing sound produced by ionization becomes louder due to stronger electrical discharges in the surrounding air. The amount of power losses also increases because more energy is wasted in ionizing the air instead of being transmitted efficiency through the line. In addition, radio interference becomes more severe, creating greater noise that can distort nearby communication and broadcasting systems. Therefore, higher operating voltages require more careful conductor design to control corona effects. If the applied voltage is further increased up to the breakdown value of where the insulation between the conductors fail completely and a flashover occurs. This results in a direct discharge path between the conductors due to the breakdown of the surrounding air. The phenomena observed before complete breakdown includes violet glue around the conductors, a hissing noise, and the production of ozone gas in the surrounding environment. In overhead transmission lines, this combination of effects is effectively collectively known as a corona. So, in summary, corona is therefore an important high voltage effect that indicates the stress condition of the electrical insulation in power transmission systems. The surface condition of the conductors play an important role in the behavior of corona. If the conductors are smooth and well polished, the corona discharge tends to be uniform along the entire length of the conductor, resulting in an even and consistent glue. However, if the surface is rough or has irregular points, the electric field becomes concentrated at those points, making the corona appear brighter and more intense in those areas. In the case of DC voltage, the corona behavior differs between the positive and negative conductors. The positive conductor typically shows a smooth and uniform glue around its surface, whether the negative conductor exhibits a more irregular or spotty glue due to uneven ionization of the surrounding air. These differences are important in understanding corona characteristics under different voltage conditions. The occurrence and the intensity of corona in overhead transmission lines are influenced by both the physical condition of the atmosphere and the electrical and mechanical characteristics of the transmission line itself. Several key factors determine how easily corona is formed and how severe its effects will be. First, atmospheric conditions such as temperature, pressure, humidity, rain, fog, and dust can significantly affect the dielectric strength of air and therefore the likelihood of corona discharge. Second, the size of the conductor is important. Larger diameter conductors reduce the electric field intensity at the surface and help minimize corona. Third, the spacing between conductors play a major role as a smaller spacing increases electric field concentrations and promotes corona formation. So finally, the line voltage is a critical factor since higher voltages increases the electric stress on the air and make corona more likely to occur. So corona is strongly influenced by the physical condition of the atmosphere because it is caused by the ionization of air surrounding the conductors. Therefore, any change in atmospheric conditions directly affects the formation and intensity of corona. During stormy or bad weather conditions, the number of ions present in the air increases significantly compared to fair weather conditions. As a result, the dielectric strength of air decreases, making it easier for ionization to occur. Consequently, corona can appear at much lower voltages during stormy weather than under normal fair weather conditions where the air is relatively clean and stable. The size and physical condition of the conductor significantly influence the occurrence of corona in overhead transmission lines. The corona uh, effect is closely related not only to the diameter of the conductor but also to its surface condition and shape. A rough or irregular conductor surface tends to increase corona formation because surface imperfections cause localized intensification of the electric field, which reduces the breakdown voltage of air around the conductor. As a result, ionization occurs more easily at these points. In comparison, a smooth conductor provides a more uniform electric field distribution and therefore experiences less corona. Furthermore, standard conductors have inherently uneven surfaces due to their construction, which leads to higher coronal losses compared to solid conductors of the same diameter. Therefore, conductor design and surface quality are important factors in minimizing corona effects. So the spacing between conductors is another important factor that affects the corona phenomena in overhead transmission lines. When the distance between conductors is made sufficiently large compared to their diameters, the likelihood of corona formation is greatly reduced or may even be eliminated. This is because increasing the spacing reduces the electrostatic stress or electric field intensity at the surface of each conductor. With lower surface stress, the air surrounding the conductors is less likely to become ionized, thereby preventing corona discharge. Therefore, proper spacing between conductors is an effective design consideration to minimize coronal losses and improve the overall efficiency of the transmission system. The line voltage is one of the most significant factors affecting the occurrence of corona in overhead transmission lines. At low voltage levels, the electric field around the conductors is not strong enough to disturb the insulating properties of air, so no ionization uh, take place and the corona does not occur. So, however, as the line voltage increases, the electrostatic stress at the surface of the conductor also increases. When this stress reaches a critical level, it becomes sufficient to ionize the surrounding air, uh, turning it into a partially conducting medium. At this point, corona discharge begins to form around the conductor. Therefore, higher transmission voltages increases the probability and intensity of corona, making voltage control and proper line design essential in transmission systems. So the phenomena uh, of corona is an important consideration in the design and performance analysis of overhead transmission lines. To properly understand and evaluate corona effects, several key technical terms are commonly used. One of these is the critical disruptive voltage, which is the minimum voltage at which the electric field at the conductor surface becomes strong enough to start ionizing the surrounding air. Another important term is the visual critical voltage, which is the voltage level at which corona becomes visible as a faint glue around the conductors. In addition, the power losses due to corona refers to the energy losses in the form of light, heat, sound, and chemical effects during the ionization process. These terms are essential for analyzing corona behavior and designing efficient high voltage transmission systems. So critical disruptive voltage is defined as the minimum phase to natural voltage at which corona first begins to appear on a transmission line. Below this voltage level, the air surrounding the conductor remains non-conducting and no ionization takes place. However, when the voltage reaches this critical value, the electric field intensity at the surface of the conductor becomes strong enough to cause ionization of the surrounding air, initiating corona discharge. For a system of two conductors of radius r in centimeter space at a distance d in centimeter again, the potential gradient at the surface of the conductor can be expressed as these equations in this slide. So where V is the phase to natural voltage when this gradient reaches the dielectric strength of air, the critical disruptive condition is achieved and corona starts to form. For corona to occur, the electric field intensity or potential gradient at the surface of the conductor must reach the breakdown strength of air. When this condition is satisfied, ionization of the surrounding air begins, leading to corona discharge. The breakdown strength of air depends on atmospheric conditions such as pressure and temperature. Under standard condition of 76 centimeter of mercury pressure and a temperature of 25 degrees centigrade, the maximum breakdown strength of air is approximately 30 kilovolt per centimeter. In terms of root mean square RMS value, it is about 21.2 kilovolt per centimeter. This critical value is denoted by G0 and is used as a reference in analyzing the onset of corona in transmission line design. If VC represent the phase to natural voltage required to produce the breakdown condition under standard atmospheric conditions, then corona will just begin to form when the potential gradient at the conductor surface becomes equal to the breakdown strength of air, G0. By equating the surface gradient to G0, the expression for the critical disruptive voltage can be derived. Thus, the critical disruptive voltage is obtained as the minimum phase to natural voltage required to initiate corona formation on the transmission line under specific atmospheric conditions. So this value is an important design parameter because it determines the voltage level at which corona effects start to appear and must be considered in high voltage power transmission system design. Okay, the expression derived for the critical disruptive voltage is valid under standard atmospheric conditions, that is at a pressure of 76 centimeter of mercury and temperature of 25 degrees centigrade. However, in practical situations, these conditions are not always constant, and changes in atmospheric pressure and temperature lead to variations in the air density, which in turn affect the dielectric strength of air. since the breakdown strength of air G0 depends on how densely the air molecules are packed. Any change in air density will directly influence its value. In general, G0 is directly proportional to the air density factor, meaning that higher air density increases the breakdown strength while lower air density reduces it. So this variation must be considered for accurate corona calculations in real transmission line conditions. At barometric pressure of B centimeter of mercury and a temperature of T in degree centigrade, the breakdown strength of air changes due to variation in air density. Under these non-standard conditions, the effective breakdown strength becomes delta G0, where delta is the air density factor. The air density factor, delta, accounts for the combined effect of pressure and temperature and is given by the relation as you can see in this slide. So under standard atmospheric conditions, it means B is equal to 76 centimeter of mercury and T is equal to 25 degrees centigrade. The value of delta is equal to 1. Therefore, the critical disruptive voltage under actual atmospheric conditions is adjusted using this air density factor, showing that corona formation is strongly depend, dependent on environmental variations in pressure and temperature. So a further correction is required to account for the surface condition of the conductor, since real conductors are not perfectly smooth. Surface irregularities such as roughness, dirt, or strands in stranded conductors increases the electric field concentration and reduce the effective breakdown strength of air. To include this effect, an irregularity factor M0 is introduced. This factor is used as a multiplying coefficient in the expression for the critical disruptive voltage. Therefore, the modified expression for the critical disruptive voltage will be this equation, as you can see here in this slide, where M0 represents the surface irregularity factor of the conductor. For a perfectly smooth conductor, M0 is equal to 1, while for rough or standard conductors, M0 is less than the 1, indicating a reduction in the disruptive voltage level. This correction ensures more accurate prediction of corona onset in practical transmission line conditions. Okay, visual critical voltage is defined as the minimum phase to neutral voltage at which the corona glue becomes visible along the entire length of the line conductors. At this voltage level, the ionization of air around the conductors is strong enough to produce a noticeable luminous effect typically seen as a faint violet glow. It has been observed that in the case of parallel conductors, the corona phenomenon does not become visible immediately at the critical disruptive voltage VC. Instead, the visible corona starts at a higher voltage level VV, known as the visual critical voltage. So this occurs because a certain level of ionization intensity is required before the glue becomes detectable to the human eye. So therefore, the visual critical voltage is always greater than the critical disruptive voltage and plays an important role in practical observation and analysis of corona effects in overhead transmission lines. So the phase to natural effective value of the visual critical voltage is determined using an empirical relation that accounts for both atmospheric conditions and the surface condition of the conductors. This expression incorporates a, correction factor to better represent practical operating conditions in overhead transmission lines. In this formula, MFV is introduced as the visual irregularity factor, which adjusts the voltage level at which the corona glue becomes visible. For perfectly polished and smooth conductors, MAV is equal to 1, indicating no reduction in performance. However, for rough or imperfect conductors, the value of MAV typically ranges from the 0.72 to 0.82, reflecting the increased surface irregularities that influence corona appearance. So this empirical relationship is widely used in transmission line designed to estimate the voltage at which visible corona will occur under real world conditions. Okay, power losses due to corona is an important consideration in the design and operation of overhead transmission lines. When corona is formed, electrical energy is continuously consumed in ionizing the surrounding air. This energy is not transmitted to the load but is instead dissipated into the environment in different forms. This includes light, which appears as a faint glow around the conductor, heat due to the energy released during ionization, and recommendation of air molecules. Sound typically heard as a hissing or buzzing noise, and chemical action, mainly the formation of ozone and nitrogen oxides in the surrounding air. Although the power losses due to corona is generally small under fair weather conditions, it it can become significant at high voltages or under adverse weather conditions. Therefore, minimizing coronal losses is essential for improving transmission efficiency and reducing unwanted environmental effects. This slide also presents the empirical expression used to estimate corona power losses in overhead transmission lines once the critical disruptive voltage is exceeded. The losses is captured by the following relationship you can see in this slide. So this equation highlights how coronal losses depends on both electrical and physical parameters on the system, especially the supply frequency F increases the losses, reflecting a greater ionization activity at higher frequencies. The air density factor, delta, um, delta, delta accounts for atmospheric conditions such as pressure and temperature, meaning corona effects are more pronounced at lower air densities. It means high altitudes. The geometric term SQRT D shows the influence of conductor radius r and spacing d, where larger conductors and greater spacing help reduce losses. Most importantly, the losses varies with the square of the voltage difference V minus Vc, indicating that once the operating voltage exceeds the disruptive voltage Vc, coronal losses rise rapidly. Overall, this formula is essential for predicting and minimizing energy losses in high voltage transmission design. Okay, this slide introduces an important practical perspective on the corona phenomenon by emphasizing that it is not purely harmful or beneficial, but rather a double-edged effect in high voltage transmission systems. Corona offers certain advantages, such as reducing the severity of lighting surges and transient overvoltages by dissipating energy into the surrounding air, which can improve system protection. It can also act as a natural voltage equalizer along the conductor surface. However, these benefits come at a cost of several disadvantages, including power losses, audible noise, radio interference, and gradual insulation deterioration due to ionization. Therefore, in the design of overhead transmission lines, you must carefully balance these competing effects. The goal is to minimize the negative impacts while still taking advantages of the protective characteristics of Corona, leading to an optimized and reliable system design. Okay, this slide focuses on the key advantages of Corona in overhead transmission lines and explain how it can positively influence system performance. When Corona occurs, the air surrounding the conductor becomes partially ionized and behaves like a conducting layer. This effectively increases the residual diameter of the conductor, which in turn reduces the electric field intensity and electrostatic stress between conductors. So as a result, the likelihood of insulation failure is lowered. Additionally, Corona plays a beneficial role in mitigating transient effects such as lighting or and switching surges. By dissipating some of the surge energy into the surrounding air, Corona helps smooth out sudden voltage spikes, thereby improving the overall stability and protection of the transmission systems. So this slide highlights the major disadvantages of Corona in overhead transmission lines, emphasizing its negative impact on system performance and surrounding infrastructure. One of the primary drawbacks is the losses of energy in the form of corona discharge, which directly reduces the transmission efficiency of the line. In addition, corona produces ozone due to ionization of air, and this ozone can chemically react with conductor materials, leading to corrosion and long-term deterioration. Another important issue is that the current associated with corona is non-sinusoidal, which introduces distortion in the voltage waveform and results in non-sinusoidal voltage drops along the line. This distortion can create electrostatic interference, particularly inductive interference with nearby communication lines, thereby affecting signal quality and reliability. Overall, these disadvantages must be carefully considered and minimized in transmission line design. Okay, this slide discusses practical methods for reducing the corona effect in high voltage systems, particularly at voltage levels of 33 kilovolt and above, where corona becomes significant. At these voltages, the electric field around conductors can exceed the critical value, leading to ionization of air and the formation of corona. Therefore, careful design of substations and bus bars is essential to control electric field intensity. If not properly managed, the presence of highly ionized air can increase the risk of flashover across insulators or between phases, um, potentially causing severe damage to equipment and compromising system reliability. To mitigate this risk, you typically employ strategies such as using conductors with larger diameters, increasing spacing between conductors, and shoring small conductor surfaces to avoid localized electric field concentration. Overall, the slide emphasizes that proper design is crucial to safely operate high voltage systems while minimizing corona related problems. So this slide explains one of the most effective methods for reducing corona effects in overhead transmission lines, namely increasing the conductor size. When the conductor diameter is increased, the electric field intensity at its surface decreases for the same operating voltage. As a result, the critical disruptive voltage at which corona starts is raised, meaning that the line can operate at higher voltages without initiating corona discharge. Consequently, corona-related issues such as power losses, noise, and interference are significantly reduced. This is why conductors with larger cross-sectional area, such as aluminum conductor steel reinforced, are widely used in high voltage transmission systems. Overall, the, the slide hides that selecting an proper conductor size is a key design strategy for improving efficiency and reliability while minimizing corona effects. Okay, this slide presents another important method for reducing corona effects by increasing the spacing between conductors. When the distance between conductors is increased, the electric field intensity around each conductor is reduced, which in turn raises the critical disruptive voltage at which corona begins. As a result, the likelihood of corona formation is minimized or even eliminated under normal operating conditions. However, this slide also highlights an important practical limitation. Increasing conductor spacing leads to larger supporting structures, such as longer cross arms and stronger towers, which significantly increases the overall cost of the transmission system. Therefore, in engineering design, an optimal balance must be achieved between reducing corona effects and maintaining economically feasibility. Okay, this slide presents a practical example for calculating the disruptive critical voltage of a three-phase transmission line using standard corona theory. The given data include conductor diameter, spacing, air density factor, and surface irregularity factor. First, the conductor radius and spacing are converted into consistent units, and the electric strength of air is adjusted to its RMS value. The disruptive critical voltage per phase is then determined by using the empirical formula as we had previously by using of this equation. By substituting the given values, the phase voltage at which corona starts is calculated as approximately 83.64 kilovolt. Finally, this phase voltage is converted to the line voltage using the three-phase relationship. So we just need to multiply by square 3, resulting in a disruptive critical line voltage of about 144.8 kilovolt in RMS. So this example clearly demonstrates how conductor geometric and environmental factors influence corona inception and highlights the importance of accurate calculations in transmission line design. This slide explains how to determine the spacing between conductors in a 132 kilovolt transmission line when corona discharge begins at a line voltage of 210 kilovolt RMS. The conductor diameter is given as 1.956 centimeters, so the conductor radius is calculated as 0.978 centimeter. Since the ionization potential gradient is 30 kilovolt per centimeter, the dielectric strength of air under RMS conditions becomes 22.2 kilovolt per centimeter after dividing by square 2. So assuming the line is a three-phase system, the disruptive voltage per phase is found by dividing the line voltage by square 3, which gives 121.25 kilovolt. For smooth conductors, the irregularity factor is taken as 1, and under standard atmospheric conditions, the air density factor is also assumed to be 1. Using the disruptive critical voltage formula for corona, the relationship between voltage, conductor radius, and spacing is established. Substituting the known values into the equation gives the logarithmic term ln d over r is equal to 5.848. So solving for d results in a conductor spacing of 338.92 centimeter. Therefore, the required spacing between conductors to avoid corona below the specified voltage is approximately 3.39 meters. Okay, this slide explain the calculation of corona power losses in a three-phase 220 kilovolt 50 hertz transmission line, where the conductors have a radius of 1.5 centimeter and are spaced 2 meters apart in an equilateral triangular range arrangement. The atmospheric conditions are given as 40 degrees centigrade temperature and 76 centimeter of mercury pressure, while the irregularity factor is taken as 0.85. First, the air density factor delta is calculated using the standard formula, resulting in a value of 0.952. The dielectric strength of air is assumed as 21.2 kilovolt per centimeter RMS. Using these values, the critical disruptive voltage per phase is determined by applying the corona inception voltage formula, giving VC is equal to 125.9 kilovolt. The supply voltage per phase is calculated by dividing the line voltage by square 3, resulting in 127 kilovolt. Since the operating voltage is slightly higher than the critical disruptive voltage, corona occurs and power losses must be calculated. By substituting all values into peak empirical formula for coronal losses, the coronal losses per phase is found to be 0.01999 kilowatt per kilometer. So finally, for the complete three-phase system, the total coronal losses becomes 0.05998 kilovolt per kilometer. So this shows that coronal losses is relatively small in this case because the operating voltage is only slightly above the disruptive critical voltage. Okay, this slide explains how to determine the disruptive critical voltage and the coronal losses at a new operating voltage for a three-phase equilateral transmission line. The line is known to have a coronal losses of 53 kilowatt at 106 kilovolt and 98 kilowatt at 110.9 kilovolt. Since the frequency, air density factor, conductor radius, and spacing remains constant in both cases, the coronal losses formula shows that power loss is directly proportional to the square of the difference between the phase voltage and the disruptive critical voltage, meaning P is proportional to this equation. Okay. First, the line voltages are converted into phase voltages by dividing by square 3, giving 61.2 kilovolt for 106 kilovolt and 64 kilovolt for 110.9 kilovolt. Using the proportional relationship for the two known coronal losses, the equation, uh, we have these simple equations, and finally Vc is equal to 54 kilovolt. So next, to calculate the current losses at 113 kilovolt, the new phase voltage is found as 65.2 kilovolt. Again, using the proportional relationship, we can find a new value for W. So this example shows how coronal losses increases rapidly as the operating voltage rises above the disruptive critical voltage. Okay, thank you so much for your attention. And most of examples and materials are coming from this book. So thank you so much.